Hello and a warm welcome, everyone, to Researcher's Desk. It's lovely to have all of you here, and it's also really nice to welcome Léon Chafik from the Department of Meteorology at Stockholm University, who's going to talk to us about climate anomalies in the North Atlantic Ocean. I've heard you before, Leon. I know you're an excellent speaker and your research is really, really fantastic. And we really appreciate you taking the time to be with us today. What I'm going to do now is I'm going to turn my own camera off. I'm going to be in the background. If there's any technical issues, I'll just pop up. But that's so that we get a really nice recording and that everyone sees everything properly. Leon, a warm welcome to Researcher's Desk.
Thank you so much, Alistair, and I hope you can hear me very well. Um, so,
We
uh,
can.
and thank you so much for this invitation. I know that Freddie Shank talked about the Atlantic Meridional Overturning Circulation, or what we call the Gulf Stream system, a few months ago. So hopefully, I will give you another take on this topic, especially looking into the anomalies in the North Atlantic Ocean. And so, by anomalies, we mean those um, temperature or salinity uh, strong deviations from the time mean. And I guess you've all seen this beautiful picture of the ocean circulation. It's of course very, very simplified. It is what we call the Great Ocean Conveyor Belt. And I hope also you can see my cursor. Um, And this tells you, when you look at it at first glance, that the ocean basins are connected. The cold waters upwells in the Pacific Ocean, and it returns via Indian Ocean into the Atlantic. But when you look at the Atlantic Ocean, you can see that there is warm surface waters all the way from the South Atlantic all the way to the North Atlantic. And this doesn't happen in any other basin, um, any other ocean basin. And this is really the heat that is conveyed to our latitudes and keeps Scandinavia and Europe warmer than average, especially during winter time. And so this is the topic that's been highly debated and it's still debated. So how is this circulation changing over time, and especially what are the effects of global warming on this circulation? Another view of this circulation, when we delve into a little bit of the details, is this is of course too many details here. You see I just want to highlight this is our observations showing the red means the northward velocities. So as you can see at the surface, there are uh, many branches or surface northward velocities, bringing this heat to higher latitudes, and this heat also cools and returns um, at the western boundary southward. So this is a very simple surface picture where what we oceanographers like to do when we actually talk about AMOC is collapsing all these velocities at every latitude, and this gives you something we call the stream function. So a stream function, this is what is shown here on the side. This basically portrays that you have um, waters that are moving northward at the surface, they sink and they move southward. Um, and so when average these velocities, you can actually get a measure, an estimate of how strong this circulation is. And so let me just um, and as I said, the real reason why we care about this is because of the heat transport. So from a climate perspective, we're interested how this heat that moves northward has changed over time. And I know that there are non-specialists in the room here. So what I will do, I will try to show how we can calculate easily this heat that will move, that is moving northwards. So of course, we care about the heat transport. That is kind of the essence here. And you can do a simple calculations to get at how much heat is actually moving towards higher latitudes. So you can the heat transport you can basically formulate it as the density of the waters, the heat capacities, and the temperature difference between this surface waters that move northwards and the cold water that moves southwards. Um, and then the AMOC is how much the how much water is actually transported. Usually we use the term or the unit Sverdrup, which is 1 million cubic meters per second. And so if you do this simple calculation, you end up with zero point 0.9 petawatts. So this is a very simple way of calculating how much transport moves northward in the ocean, or in the Atlantic Ocean. And this compares very well with other estimates, observational estimates. So here are about zero point 0.9 petawatts here, and all of these different symbols here show different direct observations of this heat transport. So, and you can see where with this simple formulation gives you about zero point 0.9. This is very well compare very well with other estimates from direct measurements in the ocean. So how much is actually this zero point 0.9 petawatt? I've tried to make a very simple analogy here by doing some back of the envelope calculations. So about 1 petawatt is really a huge number, and each reactor at Sweden's largest power plant has a rating just over 1 gigawatts. So 1 petawatt can translate to 1 million big nuclear power reactors. And according to Wikipedia, there are 413 that are in operation in the world, 92 in the US. So it's really a huge heat machine that moves this heat northward. And that's really why we care about if it's changing and how much it's changing and what are the factors that's making this machine change. And as I said already in the beginning, and I think all of you know about this, is we care about this heat that moves towards high latitude because of the mild climate that we experience in Scandinavia as compared to other latitudes. So this is a simple analysis where you can take the winter temperatures. You can look how much every point deviate from kind of the zonal mean, and you can see that during winter time, Scandinavia is much more temperate, have experienced milder climate than, for example, North America. So this heat that is brought northward towards our latitude is released to the atmosphere and leads to, climatologically speaking, a milder climate over Scandinavia. And of course, we want to understand how this system is changing, since it is the leading factor behind the climate that we experience here. So one of the things to understand how this heat is what could impact this heat. So now we've looked at the heat transport. We know that is about 1 petawatt. So you have that in the back of your mind. So this is a heat transport here. This is latitude. And this is a model simulation. So this is how the heat looks like. It peaks in the subtropics, and then it declines as we move towards higher latitude. So this is climatologically speaking, this is what you should see in the structure of the heat transport. But imagine that you dump a lot of fresh water into the North Atlantic. So you can do this in the model world, where you can add fresh water into the North Atlantic, and you can see how does the system respond to that. And and clearly, as you see here by in the red curve, we move from 20 Sverdrups, that is 20 million cubic meter per second, to about 3.4 Sverdrup. Okay, so that's a kind of a fifth, um, one-fifth reduction in the AMOC. And in the heat transport, we're moving from around 1 petawatt to about zero point 0.2 petawatts. So that's kind of a huge reduction in the heat transport by adding fresh water to the system. And you can see here how much how the climate. This is just the surface temperature change after you add this fresh water to the system, and you can see after 10 years, 20 years, 30 years, and 40 years, there's a huge, not only a cooling over Scandinavia, but it's actually this is a strong global signal here. And again, this is really why we are trying to understand how the system is changing, because it has such a huge impact globally. And you can also move to much more extreme climate change, and this is some studies that's been done on by abrupt changing the CO2. So this is a 4 times CO2. Um, you do an abrupt change in the CO2, and you can see how the system reacts to changes in the CO2. Um, and there's a lot of details here. This is, as I mentioned in the beginning, this is how we look at the circulation. This is the stream function. It shows that heat moves northwards here, and it sinks and moves southwards. And so this is the control. This is kind of the climatology in the model. And when you add and when you abruptly change the CO2, after many years, you can look at how the system has changed, and you can see that there's less red in this panel, meaning that when you take the difference between abrupt 4 times CO2 simulation and the pi control, you see there is a huge reduction in the in the AMOC strength in this heat that is transported northwards. And again, this is largely due to the fresh water. So in the CMIP, uh, models used by the IPCC, they show a clear relationship between how much fresh water there is in the North Atlantic and the strength of the AMOC. So this is shown here. This is the density. So density is a function of temperature, but largely also but largely salinity. And you can see there's a clear relationship between how much fresh water there is in the North Atlantic and how much the AMOC changes in percentage here. And when you can delve in a little bit more uh, into the dynamics or the physical processes, and you can simply think of this is the and this arrow which portrays the North Atlantic current that moves heat northwards. And as you dump a lot of fresh water in the North Atlantic, you change the gradient, this difference in the density across this current that moves heat. And so, as you know, in the atmosphere, the pressure gradient that's related to how much wind. And this is the same thinking that you can apply here, is that the difference in the densities across the current will lead to a change in the strength of the current, and hence the heat that moves northwards. So what has happened over the observational period? Now, I've just been talking about these model experiments, and I gave you a little bit of the physics behind what could happen. So let's delve in a little bit into observations. Um, and I think I usually like this plot here because it tells you that there is heat actually moving from the North Atlantic all the way to the Arctic Ocean. So you all know that the Arctic has been warming, and the ocean heat transport is one key factor. This is we've been seeing an increase in this warm pulse in the early 2000s, and this warm pulse that has its origin at lower latitudes was traced around the Arctic Ocean. So you can see here in the Fram Strait between Svalbard and Greenland, you can see how this heat, and this is the purple colors, has been increasing over years since 1997 all the way to 2009. Also, you can take another section from observations just northeast of Svalbard, even in the Laptev Sea, in the Amazonian Basin. And so this tells you that the heat, so heat changes in the heat transport at lower latitudes um, affects what happens in the Arctic Ocean. And so any change to that heat transport will be reflected in what is happening at higher latitude. And so let's take a look at how this heat transport has changed, and a little bit of the spatial pattern. So this is from a study that was done a while ago, showing observations of the heat in the upper ocean between 1986, 1990, 1991, 95, 96, 2000, and 2001, 2005. And these are pure observations here. And bluish means that it's colder than average. Red means that warmer than average. And you can clearly see that with time over these 5 year periods, there is an increase of the temperatures, but also that the temperatures progress northward slowly. And this is the heat that I was just talking about in the Arctic Ocean. So Tsubuchi et al. Looked at this heat and how it's changed over observational period since the mid 90s. And one of the things that you see clearly in this, so this shows heat transport in the y-axis, time on the x-axis, and there was an increase in until 2000, and kind of a steady plateauing of the heat transport. But this doesn't show any, even if the um, this is just really limited period. Doesn't tell you how the heat transport has changed over time, but it tells you that over this period, 90s and 2000 and 2000 teens, there was an increase in the heat transport. And this is what we've done to try to give some context, um, kind of a long-term context to the heat transport. This is the work that I've done with some of my colleagues to reconstruct the heat that is actually at the just at the Greenland-Scotland ridge, so it's between Greenland and Scotland. And I don't have to go into the method here, but basically when you use only observations and try to reconstruct this heat transport, it doesn't show any sign of a decrease since the 1900. So there are a lot of gaps, of course. You can trust it from 1950, but since 1950 there is no change in this heat in this meridional heat transport. And so this is against goes against the thinking that the AMOC should change or should weaken under increased CO2 or under global warming. It when you look at the variability, largely the variability of the heat transport, it coincides what we call the Atlantic multi-decadal variability. So when the entire this is an index that tells you about how the entire North Atlantic changes from between different decades. So between 1920 1950 there was a generally the Atlantic was warmer than average. Between so 60s 70s until the early 90s, the North Atlantic was colder than average, and then there was an upturn again since the 90s, mid 90s, and this is similar to what this study has also shown. So there's a very strong multi-decadal variability in the North Atlantic. Largely, this multi-decadal variability is set or determined by controlled by the ocean circulation. And we can also take a look. So I just showed you now temperatures. I didn't show you trends. I just showed the evolution. And there's been very strong decadal changes in the North Atlantic since the mid 90s. So the upper panels here show the temperature trend in the upper ocean. Um, so this is Celsius per year. This is for 95 2007. There was an increase in the temperatures, so the clear temperature trend. Between 2007 2015, there was actually a cooling um, during this decadal period. So uh, we know that in this region, which we call the subpolar North Atlantic, there are very strong decadal changes. And the physics behind these decadal changes, I would say, are rather understood, but they are um, they they differ between different events, so to say. Um, so not only in the temperature we've seen these strong changes, we also see changes in the salinity. So there was a strong increase. So with the warming, there also is much warm, more saline waters. So the salinity also increased during this first period. And there is this second period, 2007, 2015, there was a freshening. Um, and And we did look into this freshening in another study. And so this is what is shown here. This is salinity anomaly with time and salinity anomaly on the y-axis in a region just south of Iceland. And from this you can and we use this is really a collection of many observations, multiple platforms from ships, direct measurements, and perhaps this is the longest time series that we have in of salinity, so surface salinity. And you can see a lot of fluctuations on many time scales, so from decadal to multi-decadal. So for example, in the 70s, we know that there was a large change in salinity, which was called the Great Salinity Anomaly. And you can see here again what I just showed, that there was an increase in the salinities um, in over from the 70s towards the mid 2000, and then there was a large change in the salinity. So a large freshening signal that was seen since 2016. This is the largest signal over this 120-year period. And I guess you're already thinking how this freshening affected the heat transport and the AMOC. And I will come to that just in a second. Um, so again, here is this time series that I just showed you. Again, you can see the different variabilities, and here you can see this is the in 2020 we had the freshest signal in 120 years, and we understand that ocean circulation caused part of this signal. So, for example, what we put forward in this paper, there was a huge shift in the ocean currents. So this is what it portrays. This is what this plot portrays. Usually, you have fresh waters that moves along the shelf or the coast, all the way along the North American coast southward, and there was a change in the atmospheric circulation during that period, 2014 2016, that led this freshness signal to actually being rerouted into the open ocean. Uh, so instead of continuing southward, it was a rerouting of this this fresh signal that moved a lot of this fresh waters into the open ocean. And associated with that, there was large changes in the North Atlantic current. So what we call the Gulf Stream in this region. As a result of that, there was less fresh waters moving southward, there was also an increase in the salinities in northwestern shelf seas of North America. So ocean circulation and changes in the caused by changes in the atmosphere really caused a big change in the salinities. And we have been monitoring the AMOC at these latitudes, especially between Scotland and Greenland and Canada, where we have measurements down to the bottom across these latitude to actually get an estimate every month of the AMOC. And without going into the details, we actually did not see a huge change in the AMOC despite this very, very strong change in the fresh waters or the freshening. Um, this is a study that came out last year that was discussing that different methods could lead to different trends. So if you use one method, it only gives you zero point 0.5 Sverdrup. This is so again, Sverdrup is million cubic meters per second. If you use another method, it's minus 2 Sverdrups. But it's kind of the take home point is that despite these big changes in the water masses, there wasn't actually huge changes in the AMOC. So again, it really shows how complicated this system is really, and perhaps how resilient it is. And so coming back to the 90s and the future, now we'll talk a little bit about future changes. Um, so it's all about the ocean densities. How much we change the ocean density, because the densities are that what cause the waters to densify and move towards depths and return backwards, sustaining this ocean circulation. And so we think that the 90s was, even though we had cold, fresh Arctic outflow, there was at the same time and warmer saline waters moving northwards. So this is kind of a mean picture of the 90s. And and if the AMOC were to change in 2040s, this is what could be these are the main factors. So will have as the Arctic warms, there will be more outflow of fresh waters. Um, in 2040s, that will lead to more fresher waters. At the same time, as the circulation keeps weakening, there will be less subtropical warm waters that are warm and saline towards high latitudes. So an increase of the Arctic fresh waters, reduce Atlantic inflows, and that will also weaken the how much heat losses are lost to the atmosphere, because the fresh water will act as a lid, so less water will mix down, and in turn that will feed back on the circulation and weaken it further. And so you can take a look at it uh, as an estimate over time. So over the historical period until now, there hasn't been any change. So this is from models, multi models, so a huge number of models. Um, and again, this is the black line is the observations at one place. I should remember that the AMOC is different or has a different variability depending on where you are in latitudinal space. So it doesn't mean that one measuring at one place is enough, because that variability is different from what is happening at other latitudes. And that's really key to keep in mind, and that's the reason for measuring at different latitudes. And if we would go to this situation that would then increase a freshening, this is what we expect in the future, that there is a decline in the AMOC. And as I said, the couple of things that I just said now, we need to measure at different places, and maybe that the AMOC is actually much more resilient than we think. And this is a study we've done, came out a couple of years ago. Uh, we looked at specifically the AMOC at higher latitudes, especially the Nordic, what we call the Nordic seas AMOC. So this is between Norway and Greenland. You can do the same analysis. You have models and observations. And in this case, because we're looking into the future, we're using um, models here. And and if you do this in the usual way, and the I don't know how to go into the methods here, but the blue colors here is what how we typically calculate this AMOC. Um, and this will tell you that there was no change until 2020 or so, and then there is a decline until 2100. But if you change the way you actually calculate the circulation, which is a bit more complicated, but what you essentially do is you one of the things you see when you look at the ocean currents here is that the northward warm surface waters and the cold deep waters are on top of each other, are and also they are confined to the western part of the Atlantic, what we call the western boundary. As you move towards the higher latitudes, suddenly you see that there's an important horizontal separation between the currents. So the warm waters move in the eastern part, it densifies, sinks, and moves southward along the western part. And so when you take into account this formulation or the how the ocean currents are aligned, you formulate the AMOC in a different way, and that what actually did happen is we're seeing that the AMOC is declining in this new way, but it also recovers in the future. So simply what I'm trying to say, I know there are a lot of details here. Simply what I'm trying to say is that you the AMOC definition really matters, especially as we move towards higher latitudes. How we define it mathematically really matters how the AMOC is going to, or how we look at it in the future will differ. And so, a couple of kind of take-home message from this paper is that the Nordic Sea is overturning. This is so the AMOC at higher latitudes in the Nordic seas could be a stabilizing factor in a weakening AMOC. So if the AMOC weakens at lower latitudes, but at our latitudes, it's still it recovers. It could stabilize what's happening at lower latitudes, and most importantly, that the current changes in the North Atlantic should not be extrapolated to the Nordic seas or higher latitudes, because as I said before, that the AMOC is not really um, we cannot measure it or make claims about the entire AMOC from just one place. This needs to be done in many latitudes throughout the Atlantic Ocean, especially on the human time scale. So on our time scale, this is especially important. Perhaps this is different once you move to millennial time scales, where maybe the entire system is changing coherently. But on our time scales, we cannot um, make claims of how the AMOC is changing from one latitude. I hope there weren't too many details here and that the key messages were clear. So okay, I will just summarize at least what we think we know. Um, we know that so this is from a little bit of from an Arctic perspective, because it's really an essential factor in these um, processes and feedbacks. Human-induced climate change has had an impact on the Arctic Ocean. I think most of you agree with that. Um, we think that an increase in the freshwater content at higher latitudes will lead to a reduction in the strength of the AMOC. This is what the models show. It is anticipated that the AMOC will experience a decline in its strength in the future, and this is what the models show and what the kind of the physics from a physical understanding and increase in the freshening will lead to a decline in the strength of the AMOC. However, changes observed, so from the observations in the AMOC across latitudes so far cannot be attributed to anthropogenic climate change. And the simple answer is because internal variability is so strong of the system. This natural variability is so strong that it's really hard to actually extract any signal that can be attributed to climate change. So maybe, as I said, the AMOC is resilient, and we still haven't um, come to the point when we're seeing a critical change. Um, and from my kind of what I do every day is I think that the investigating the timing and mechanisms through which Arctic climate change will influence the AMOC, as well as the impact on the shelves and coasts where we live. I think it's something that I think we should given high priority, because at the end of the day, we really want to know how these changes will impact in a warming climate, how it impact the impact our climate, our coast, but even the ocean ecosystem as well. And I will stop there.
And I will thank you, Leon, for a really informative and talk. Thank you so much for sharing your knowledge with us.